Okay, so this morning we have Wednesday. We have Jeff Lynn right here, and Dave Andrus, and is Brandon here? Hi, Brandon. Brandon Wolfon will talk about that. So we have neutron scattering, talk about Jeff Lynn, who's a local guest from NIST, and I believe he'll be involved in the tour.
Yeah.
Tour of the department tomorrow. And Dave Andrus is from University of Tennessee near Oak Ridge, and Brandon along this here. And then after lunch, we're going to have a discussion about career advice and guidance. So hopefully, all the speakers will stick around for that. Any questions or tell you some funny jokes or whatever you like. And the last practical sessions of this afternoon. Okay. So one thing about tomorrow's tour, I will give them to you tomorrow, but there's some sheets you have to fill out about just information. One's about COVID. Actually, I think they're both about COVID, so you have to sign a sheet. So I'll give you those tomorrow. And okay, more announcements to come later. So Jeff,
Okay.
thanks for coming. And please go ahead.
I live here, so it's okay. Okay, so here's the outline. First is talk about the scattering basics, and of course you've already seen some of that from Colin Brown on the start. I'm going to focus mostly on elastic scattering because I knew that he was going to talk mostly about inelastic scattering. And so I'll talk about the cross section, and then powder diffraction, and both to get crystal and magnetic structures out. Profile refinements, I'll show you an example of what we call the subtraction technique to separate out magnetic from structural scattering. And then if that doesn't work, you can use polarized neutrons that unambiguously differentiate between the two. Show you some examples of single crystal diffraction and why we like single crystals for all these purposes. And then neutron scattering has a number of different techniques, as does X-rays. And so, at the national facilities, we have like 30 different instruments to do all sorts of different measurements. So small angle scattering is one. Scattering, when you think about scattering, if you look at a nucleus, compared to 1 angstrom wavelength of a neutron or X-ray, the nucleus looks like a point particle. And you describe that mathematically as a delta function. Fourier transform a delta function and it's a constant. So things that are big in real space, you Fourier transform it, will scatter at small angles. So we have special instruments to do small angle scattering. To look, for example, at nanoparticles, vortex lattice, ferromagnetic superconductor skyrmions, things like that. Reflectometry, I'm not going to talk very much about this because you're supposed to be growing single crystals, not thin films. So but it does exist for thin film research. Thin films are multi-layers, and you get a structural profile of the thin film and a magnetic depth profile. And then I'll talk a little bit about inelastic scattering to look at phonons, magnons, spin ice, spin liquids, things like that. And I'm going to give you some reference materials. Okay, so the main message is for scattering, what you do is you have an incoming flux of electrons or X-rays or neutrons, and then they scatter from your sample and end up in your detector. You're measuring a process. You need to know how many particles coming in, how many end up in your detector. Okay, and of course, modern instruments have many detectors. And so to describe the scattering process, you have a momentum transfer and an energy transfer. If it's elastic scattering, the energy incident and final are equal. That means that the length of Ki and Kf are equal, but in a different direction. So that So that's how you figure out what happened in your sample is measuring the change in momentum and energy of the scattered particle, X-ray region. And then I think Colin showed a version of this, but you have a function of the atomic coordinates and the magnetism in the system, and everything is contained in that function. That's what you'd like to measure. Okay, so you have a periodic array of atoms in real space, and that gives you a reciprocal space. You have a d spacing, and of course you have many different d spacings. This is the largest d spacing. It's just the nearest neighbor, and so that will give you bragg spots in reciprocal space, and then you can tune your spectrometer to go out and measure around the bragg spot or at a bragg spot. So this is always the conversion between real space and reciprocal space. And the spacing here is just 2 pi. So you have a momentum, and usually we in momentum we just drop the h bars there, and energy usually use milli-electron volts. And so you have a reciprocal space here, and you have a reciprocal lattice vector, which in this figure is called tau, and that points up to here, and Q can be off of that, and then you have a reduced wave vector. And you remember that in a periodic solid, if you have an electron, you want to know the band structures of the electron. The energy bands are periodic in reciprocal space. So if you're measuring the electron band energies, you can choose any reciprocal lattice point, and then you can measure this reduced wave vector, which is away from the Bragg point. And the eigenvalues are just periodic in reciprocal space. The eigenvectors, which give you the intensities of, in this case, the scattering for X-rays or neutrons or electrons, if you're doing electron scattering. Those are different, but remember that the energies are always periodic in reciprocal space. So you can choose any place to look for the excitations if you're looking for spin waves, phonons, that. Okay, so here are some conversions to compare the different techniques. Neutron is 1 angstrom. Here is comes in with an energy of 82 milli-electron volts. X-rays, if you do it in millivolts, then it's 11 million millivolts. So that makes life difficult in doing inelastic scattering, but you can actually do it. And then here's an electron. And then the conversion factor is 1 milli-electron volt in thermal energy is just 11.6 degrees. So room temperature corresponds to about 25 milli-electron volts. So the nice thing about neutron scattering is the neutrons typically coming out of a spallation source or a reactor. They're thermalized, they're coming out of thermal energies, and that's typically just the types of energies you want to have in order to look at collective excitations. Okay, so you will go tomorrow to the NIST Center for Neutron Research. We have a 20 megawatt heavy water reactor designed specifically for neutron scattering. And the way it works is you have a neutron that hits the nucleus at the fissions, and you get about 2.5 neutrons for each fission. Then you need to thermalize them because they're coming out with MeV of energy, but it's big M, millions of electron volts. And you need to thermalize them down to milli-electron volts. So you need a moderator, for example, like heavy water, which is what we use. Oak Ridge uses beryllium, some light element, in order to have the maximum amount of energy transferred in collisions. So then if you look at the neutron velocity here, and you will have a Maxwell distribution of neutrons, roughly centered about 300 Kelvin. If you want lower energy Neutrons, you can put in a liquid hydrogen cold source. And that just takes that whole spectrum down to low energies. If you want hot neutrons, you can put in hot graphite, or a spallation neutron naturally has very energetic neutrons, and then you can spread that out into higher energies. So if you have a spallation source, you can have different sources for the different instruments, where the proton beam comes in, hits the nucleus, for example, like mercury, just basically explodes it. You get a bunch of neutrons out, and then you tailor your sources to the instrument that you want to build. Okay, so, yep, you got it.
What does it make the difference in the distribution for each of them?
The temperature. So the cold source is typically around 25 Kelvin.
Oh, you pull it down.
Yeah, right. Or the graphite is up at 2000 Kelvin. So you don't need to read this, but I just mentioned the advantages of neutrons and versus X-rays. For neutrons, the magnetic and structural scatterings are comparable in strength. So that makes life very, very nice. Elastic scattering, you can get quantitative information about, for example, ordered moments, atomic positions. Typically, energy resolution is orders of magnitude better than what you can get with X-rays. And that's just because neutrons are coming in millivolts, X-rays are coming in megavolts, millivolts. So it makes it more difficult to get the accuracy, but you can do actually very nicely with X-rays up to a point. And then for neutrons, the sample environment tends to be a lot simpler. You can use aluminum to make sample holders and things. Neutrons basically go right through aluminum. And so you can make your cryostats or furnaces very easily. You don't need beryllium windows, things like that. And you can go down to very low temperatures, down to microkelvin. And the final thing is that the theory has a very solid basis. It's neutrons are weakly interacting, and the theory has been around for a long time and it's very well developed. So you know exactly how to do that. The advantages of the X-rays, of course, is you have ultra high flux and very small size beams. So you can use small samples, you can use thin films, single atomic layers, you can study those. Do cryptography, you have the capability of doing probe capability for nonlinear. And then for magnetic scattering, resonant scattering, you can tune it to the edge. That's a new feature that's available with the invention of the synchrotron, is that you can tune the energy and then you can have element-specific sensitivity, and also you can raise the magnetic scattering so you can see it. Okay, normally when you do conventional X-ray scattering, the magnetic scattering in principle is there because X-rays are an electromagnetic wave, but it's 6 orders of magnitude smaller than the charge scattering, so very difficult. I do have a chapter that I wrote with Bernhard Keimer on magnetic scattering, both for X-rays and neutrons. I'll make that available. We're allowed to do that for students. So magnetic X-ray scattering, the way it works is you take an electron and you promote it up, for example, from a 2p level up to the 3d level, and then you have an occupied electron come back down. For 4D elements, that's a higher energy. So you go up here to the 4D shell and then back down again. And basically, the photons are categorized into 3 different energy ranges. So really soft is less than a kilovolt. Of course, these are intermediate is up to 5 kilovolts, and then hard X-rays greater than 5 kilovolts. Copper K alpha X-rays is 8 keV. So that puts some restrictions if you're interested in, for example, up in 3D, like a copper magnetic moment. You have to use soft X-rays, and you don't go very far in reciprocal space. In fact, typically you can't even get out to the first magnetic. So that's not 4D is quite a bit better. That you can typically go out further in reciprocal space. So you don't have a choice about where that resonant energy is going to come. So sometimes it's convenient, sometimes not. Magnetic cross-section for X-rays, you have charge scattering, that's the conventional one. And then you have X-ray circular dichroism, that's this term. And this is linear dichroism. This is the formula we put in the chapter, and it's for spherical scattering as the simplest case. If you have orbital contributions, crystal fields, things like that, it can get a lot more complicated. So this is kind of the structure factor, and then the intensity always goes like the square of the structure factor. Neutron scattering, you typically have 2 different contributions. So the nuclear scattering, basically the structure factor here has a scattering amplitude, because I remember that I told you that the nucleus looks like a point particle. And so there's just a number, and you don't have to worry about the spatial distribution. And you just look those up. So if you're doing, say, a profile refinement for crystal structure, that makes life easy. And then you just do the usual sum over the unit cell. Magnetic scattering, I won't go through this, but basically, if you look at the magnetic structure factor square, there's an orientation factor here that allows you to determine the direction of the magnetic moments. You can quantitatively get out the magnetic moment on each ordered site. That's the expectation value at any particular temperature, pressure, or magnetic field. There's a magnetic form factor because you're looking at the electrons in this case. And so, and I'll show you what that is. And then, of course, you can get the structure, the magnetic structure out of them from the usual phase terms. So versus X-rays versus neutrons, X-ray cross-section just goes like power of Z, basically, Z to the 4th. So I think Wei yesterday says she doesn't like to use lithium because it doesn't have very many electrons. Lithium is about an order of magnitude stronger scatterer than hydrogen. Hydrogen's only got 1 electron, and that's only if it's not ions, and it's got 0. So, and it just turns out that neutrons have an enormous cross-section for hydrogen. So that makes it very useful for looking at fuel cells, hydrogen storage, polymers, biological systems, things like that. And so as you go through the elements, it really just depends on the nuclear properties, not the charge properties. So it kind of varies all over the place, and that makes life good in the sense that if you're interested, for example, in looking at iron cobalt system, then order disorder of iron and cobalt. They're right next to each other in the periodic table. Very hard to do that with X-rays. Turns out that the scattering amplitudes are quite different for neutrons. So you have to look to see what the probe is. And nowadays, everybody uses X-rays and neutrons. Whatever is the best technique and wherever you can get neutrons. Magnetic form factor is here for neutrons. It's just a typical one. X-rays typically is quite a bit, drops off quite a bit slower with momentum transfer. The reason is, of course, that your Fourier transform the higher charge density of the atom. So you start out, if it's a 3D, say iron 3D magnetic moments, you start out with 1s and 2s, 2p, and all of those electrons contribute to the X-ray scattering. The neutron scattering only looks at the unpaired electrons. So that's an advantage that you just see those. Typically, those are the outermost electrons, the ones that are doing the bonding. And so you have this magnetic form factor that typically drops off very quickly. And in the nuclear, it's just a constant. So you don't have to worry about that at all. Okay, so reciprocal space. Here's a reciprocal space, and you say, well, what does the powder look like? Well, you twirl it in both dimensions, so you actually create spheres of scattering that are Bragg peaks. And so this is just a cut through that, and then you put your resolution inside and scan it through, and you get a diffraction. So this is actually a titanium gold alloy that we did with the rice group and the Morrison's group. So that's what that powder diffraction looks like. And if you have, for example, a glass or fluid or nanoparticles that are really small or amorphous, structurally amorphous materials, then you do get a peak, which is just the nearest neighbor distance, but you get basically a pair correlation. So that's what powder looks like. And I'll go through this pretty quickly. So here's the real space. And if you have just a spacing here, then of course you get a delta function Bragg peak at 2 pi over d. We already went through that. But then the question is what happens if you get some disorder. For example, showing here structural disorder, but you could have a periodic array and then have magnetic disorder where the spins are disordered in orientation. And what will happen is you'll get a correlation length over which the atoms look like they're ordered, but then you drop that, and what you'll get instead of a delta function is you get a width of that peak. So you can get a lot of information about the disorder. And if it's a magnetic system, for example, you can do that as a function of temperature and measure this correlation length in real space. And the width of this is just 1 over that. Same thing with time. If you have a periodic array, looks like that. And that's a period t. So that will give you an energy that's 2 pi over t, and that's a delta function. But then if you have a lifetime to it, then that will spread out and you measure that lifetime. And Colin talked about that yesterday. Yep.
What ranges of correlation length can you measure with these?
That depends on the instrument. And so, I mean, typically X-rays and neutrons are going to be different. Typically the angular resolution for X-rays is quite a bit better. So you can go into smaller, you can go in to micron size. Neutrons typically correlation ranges of 10 nanometers to 100 nanometers and maybe 1,000 nanometers. It depends on the instrument, how big your sample is, how strongly it scatters. There's a lot of different things that go into that. So if you want beam time, I should have mentioned this earlier, is that both facilities typically have a call for proposals. Right now, NIST is shut down, but we're hoping to get back up soon. But both places typically operating have a call for proposals about twice a year, every 6 months. You put a proposal in, typically 1 in 2 or 1 in 3 will get beam time. And then you go from there. And if you're interested in that, you should contact the instrument scientists on an instrument that you think is the right one. Talk to them. They may have ideas about sample environment, or this is not the right instrument, you can't do that measurement, things like that. Okay. So X-rays or neutrons, you get the crystallography, magnetism. You can use resonant X-ray scattering or neutron scattering, which is of course what I prefer. Although I've done both. Small angle scattering to look at the vortex structure skyrmions, nanoparticles, thin film reflectometry to get the magnetic and structural density profiles, and then inelastic scattering. You can get the phonon dispersions, for example, and work out then all the interatomic potentials from that. Spin dynamics, you can do the same thing. You get the magnon dispersion, you get the exchange interactions, the anisotropy, crystal fields, multi-heroics. You can use magnetostructural coupling, things like that. Okay, so here's the NCNR that you'll go to tomorrow. Typically, we got our first guide hall started in 1987, finished officially in 1994 with a cold source upgrade, and you can see the number of users keeps going up, and then we got a second guide hall, and keeps going up, and now before we were shut down, it's close to 3,000 per year. Oak Ridge, similar numbers. They have two facilities, a high flux isotope reactor, which actually is where I did my thesis work back in 19 and then the brand new source, the spallation neutron source. So that has a pulse of protons that come in, strike mercury nuclei, create a lot of neutrons. So everything is done by time of flight. Spallation neutron source, very powerful technique. Okay, and then I mentioned that NIST has 30 spectrometers of different kinds for all these different types of instruments. For inelastic scattering, typically you can go over length scales of about 6 orders of magnitude. Structure, you can go at least another order of magnitude, 7 orders of magnitude in structural size, depending if you're interested in skyrmions, that's fairly large objects. If you're interested in proteins swimming around, those are even bigger. The bigger ones are slower. Larger objects tend to move slower, and then you can go up to very high energy. Spallation neutron source can go up even much higher than this. So there's a wide range and a lot of different instruments depending on the science that you're interested in. Okay, now Wei made a fantastic statement yesterday. She said, what's really interesting is superconductivity and magnetism. And I've been agreeing for half a century that that's correct. So I thought I would tell you a little bit about superconductors and why they're particularly interesting. So if you look at the superconductor, typical superconductor, this is magnetic field applied, this is temperature. You go below a certain temperature and the system goes from metallic into a superconducting state. You turn on a magnetic field. What happens when you turn on a magnetic field? It's a time varying field. If you have a metal, you get eddy currents. But they have resistance and they quickly die off. In a superconductor, there is no resistance. So those eddy currents are actually permanent. And they, by Lenz's law, they exactly oppose the magnetic field that you're trying to apply. And then you're in a Meissner state where the magnetic field inside your sample is 0. So that's really, so it's a perfect diagram. And then if you apply a little bit more field, then the field actually starts penetrating, but it starts to penetrate in fluxes that are vortices that are quantized. So it's a fully quantum mechanical effect. And then typically you apply enough field and you go back into the normal state. The other thing about conventional superconductors is that if you try to put magnetic ions in it breaks up the superconductivity very quickly. And they typically, all the conventional superconductors follow almost, there's always some exceptions, which I'll talk about in a minute. But they come down, there's kind of a universal curve developed by Avogadro and Gorkov. And typically this critical concentration is maybe 1 or 2%. So there's almost no chance to get collective effects. So that's the standard thing. superconductivity was discovered over a century ago, and then everybody knew that you don't want to put magnetic impurities in. It took a half a century to figure out how you can pair up electrons to make them superconducting. But you have to do it in reciprocal space, not real space, because electrons repel. So it's kind of crazy that you even think that they can just pair up into an attractive state, but you can pair them up in K and minus K and spin up and spin down. And then if you put another impurity spin in, very easy to break up. So that's the conventional idea. And then there are always exceptions to the rule. And when you find something that doesn't follow the paradigm that everybody understands, then that's usually interesting physics. And the first one was back in the 1960s, which was the cerium-ruthenium-2, and you can put the heavy rare earths in up to 25–30% without killing off the superconductivity. Then shortly after that, there were Chauvel phase systems, and this is a very interesting system. You have dysprosium, and it's surrounded by sulfur, and then the moly sublattice is almost separate. So the understanding here is that the superconducting electrons that run on the moly sublattice just don't see the spin of the magnetic ion, and so they can coexist. And if it orders as an antiferromagnet, then there's no magnetization, so there's really very little interaction of the superconductivity. Those were the first true magnetic superconductors that were discovered. And then there were a couple, and I'll show you examples of systems where instead of being antiferromagnetic, they actually order ferromagnetic. And then there really is a competition. And then along came ITC cuprates, which also can have rare earths in there, and copper can also carry a spin, it turns out. And then the boron carbides, very interesting systems. And then there were a series of new ferromagnetic superconductors, most of which are not ferromagnetic, most of which are actually antiferromagnetic. And then the sodium cobalt was very, so you can vary the amount of sodium in the sodium cobalt. And the really cool thing is if you want superconductivity, it's like instant coffee. You just add water. And it's really miraculous. I mean, the C-axis is tetragonal, basically, and the C-axis almost doubles. The water goes in, you still keep your single crystal, and it goes superconducting. But like instant coffee, it's only 5 calories, so it's not.
Yeah,
like
you should remove zirconium zinc too.
What's that?
You should remove zirconium zinc too. It was experimental error.
Yeah,
That's
actually there are a lot of experimental errors, which is why I put them up there. Yeah, including this one that we studied. Yep. And then the iron superconductors came along. There also, you probably have read that there are hydrated superconductors under very high pressure, which look like they're conventional electron phonon systems, but these are systems I've worked on. And those are extremely high, 100 gigapascals. And we haven't done anything on those. So they're very tiny samples, very high pressures, very difficult to do. Okay, so I'll give you a couple of examples of ferromagnetic superconductors. One, erbium nickel boron carbide, and then we'll go on from there. How are we doing for time?
5 minutes.
Ooh, okay. So magnetic systems. I showed you what a ferromagnet looks like. If you bring in the spins, and they all have to be parallel. And you've probably never seen a ferromagnet like this. You always see them when it spins up. But yeah, but spins down just as good as spin up, as long as they're parallel. Antiferromagnetic is like this. Spin density wave is just a wave. This is a transverse spin density wave, or just a wave usually incommensurate with the underlying crystal structure. Okay. So here are the Chauvel phase superconductors. There's holmium iron sulfide, holmium iron selenide, and selenide orders at superconducting at 5.6, and then half a Kelvin, the ferromagnetism comes in. The superconductivity in the holmium sulfide is a little bit lower, weaker, and the ferromagnetism is a little bit stronger, so they behave differently. And first question is it a ferromagnet? Well, here's an example of a magnetic diffraction pattern. So you take the diffraction pattern at very high temperatures, high being well above the ordering temperatures, and then take your ground state magnetic diffraction, subtract them, because for unpolarized neutrons, the nuclear scattering and the magnetic scattering are just completely separate. And so you get this magnetic diffraction pattern with all these very nice peaks. And you notice you also have a deficit of scattering here, which tells you that the magnetic moments scatter in the paramagnetic state, but they're just Q independent. But when you subtract that off, you get a negative scattering, an absence of scattering. And then to look at the behavior of the magnetism in the competition with the superconductivity, you need to do small angle scattering, because the London penetration depth, which tells you how the Meissner effect, is typically hundreds to thousands of angstroms. And so that's a length scale that's large. You're going to look at it at small angles. You bring in a beam. You have a beam stop right in the middle of the detector, and then you get the scattering here. And here's what powder diffraction really looks like. If you have the detector that covers the entire thing, then you get this ring of scatter. And every powder peak that you measure on X-rays or neutrons is really a whole ring. And you just typically what you do is scan through here and just get a piece of that. And you notice that this is weaker and larger in size. As you cool down, here's the temperature, half the Kelvin, 0.46, 0.4, 0.29. So you can just spit that data up, and you can watch the peak grow and also move in toward Q equals 0. So it's trying to go to Q equals 0, which would be where the ferromagnet would be, but it doesn't make it. And so it maintains the superconductivity and the long-range magnetic order. With this period is about 100 angstroms. Holmium sulfide. You get this nice ring of scattering, but now you have a repeat distance of 200 angstroms, because ferromagnetism is stronger and superconductivity is weaker, and then it collapses in. And so it's re-entrant, that the ferromagnetism drives it back into the normal conducting state. So, okay, and then finally, the erbium nickel boron carbide, TC is 11 Kelvin. 6 Kelvin is where it orders magnetically, and then there's another phase transition at 2.3 Kelvin. So you look at, for example, 4.6 Kelvin, and here's an incommensurate magnetic peak that's associated with the spin density wave. And you start cooling down, and you get more peaks in there. And what happens is that spin density wave is starting to square up. And so you get higher order peaks. In fact, even at 4.6, you can see a third order peak here, but then you get fifth order, seventh order, and finally you get a kind of a square wave, and then it tries to lock in, but it can't, and it actually causes a net magnetization to develop, and then that net magnetization breaks the time reversal symmetry. You can see that in the vortex lattice. That here's at 4 Kelvin. And the vortex lattice that we measured on the single crystal, here's the pattern of it. And then you go down to 1.6, and you haven't changed the magnetic field any, but the vortices get spontaneously generated, and that shifts the peak. This crystal was about 1 millimeter by 1 millimeter and 3 millimeters thick, just to give you an idea for this, all of these data. High TC superconductors. We'll very briefly talk about this, but it's tetragonal, and you have these copper planes, square plane wave spins in the system. And I'm going to skip over these to just go to the data. But we did the crystallography. Here's an example of the crystallography. And we found that when you start cooling down, you get a splitting of the peak. So it actually goes from tetragonal to orthorhombic. That was key in order to be able to solve the first magnetic structure in this. And here's the magnetic scattering, and you can see the magnetic, there's some magnetic scattering, that little blip there. And, so we were using our high intensity position sensitive detector. And if you scale that up, you see, in fact, yeah, you got a magnetic peak here, another one here, and two more under those big peaks. So we had 5 peaks overall, and knowing that there's an orthorhombic distortion, you come up with a very simple model. It's just that the spins are parallel along the B-axis in the formerly tetragonal and anti-parallel along the A-axis, and then stacked antiferromagnetically along the C-axis. So that's the magnetic structure. And here's the magnetic ordering temperature that we measured. And my collaborator, King Ching Dai, said, I must have made a mistake when I got this order parameter out. And difficult to get the order parameter out, very weak signal. Because the structural transition is up at around 150 something. And I got 133. And he says, can't be right. Because there's no other evidence that there's anything going on at this lower temperature. But it turned out, yeah, it's really right. And so these systems, many of them have a structural transition and an order magnetically at either at the structural transition or below it. And then I want to finally just show you very quickly this single crystal. I'll show you some inelastic scattering on this as well. But you see, when you have a single crystal, you can get some really beautiful things. And that's why you want a single crystal. And the reason for that is that if you have a powder, you put a powder up there, the bright peaks that you see only come from a few of the grains, right? It just happens that if you're at a particular powder diffraction peak, there may be 100 grains that are actually Bragg scattering. The rest of them are just sitting there. And what are they doing? They're causing background. So that's basically why single crystal typically get much better data out of that. And I just mentioned spin waves. We were able on this crystal to measure the spin waves in the system up to maybe 15 millivolts, but knowing the structure and then the energetics along the 2 different directions, we could get a model and show that these excitations, spin waves go up to about 200 millielectron volts, which is of course very high. 200 millivolts is equivalent to 2000 Kelvin, and all the action is below room temperature. So both of the cuprates and the iron superconductors have magnetic energetics that are enormously large compared to the physics that's going on when it goes to the superconducting state. This crystal was 5 by 5 millimeters and half a millimeter thick. We were able to get some good inelastic scattering. I just mentioned you can also do inelastic scattering with resonant X-ray scattering, RIX. And here's one of the first examples of doing RIX scattering and then comparing with the neutron data at that time. So you can do a lot with X-rays as well. And then the final piece that's really interesting about these iron superconductors is and also cuprates is the resonance that develops in the superconducting state. And here's the temperature dependence. It just follows the development of superconductivity. And this is a magnetic exciton and really links the magnetism directly to the formation of the Cooper pairs. Now, this was obtained with 5 co-aligned crystals, a total mass of 10 grams. So that's because this scattering is pretty weak. So I just mentioned, since we're supposed to be growing crystals, thin films, typically the magnetic or the structural part of it, it's micrograms. That's tough for neutrons to do, but you can do some things with that. Diffraction, we kind of like milligram size crystals. really have to be less than 100 milligrams, depending on the details, but otherwise you can start getting extinction effects and things like that, multiple scattering that makes it complicated. So you don't want your crystals too big. Dynamics, you want gram size crystals. So the smallest one that I've ever done was a 2 milligram single crystal with one of the cuprics, because we were really interested in that. Very difficult to do that. The biggest one was 0.4 kilograms. So come on. Yeah, that's, and in fact, that was a single crystal of nickel 60 that was grown at Oak Ridge when I was doing my thesis work. So that's giving you the scale. Anything bigger than that, and we can use it, but it's always. Co-aligning crystals, the Guinness World Record, for me, is 1,115 crystals. And this was one of the spin liquid things with young Lee and graduate student at that time was Rebecca Smama. And when she was writing up the first draft, and I saw this number, because I never really, it's air sensitive, so I never actually saw the sample. And I asked her, are you sure it's 1,115? I think maybe one of the crystals fell off. And she very nicely wrote back and says, next time she's getting this, she'll count it again. Anyway, I did want to mention thin films, which is specular reflection. You come in at very small angles, and you scatter the neutrons or X-rays off the thin film or multi-layer. And here's one example of a calcium manganite and ruthenate in a heterostructural system. You get a very nice fit to the data, but what they were looking for is whether they could change the magnetic scattering by applying an electric field, and you can see that you get an enhancement of the magnetic scattering. And this has to be done with polarized neutrons to make sure that you're doing that. And then I'll mention one X-ray scattering experiment, which is a multi-layer of lanthanum nickel and lanthanum aluminate. And they had changed the number of layers, and when they had just 2 layers, they found a magnetic peak in the system. And so it was forced to be 2-dimensional and then actually ordered magnetically. When they expanded the size of the layers to 3 and 4 and up, they lost that magnetic peak completely. And that's something probably neutrons really couldn't do. You need to do resonant X-ray scattering to really see that. Okay. Okay, wrap up. Okay, so magnetic topological systems. These are the systems I worked on: spin ice, spin liquids, the cubic half Heusler. We can skip that because that was with JP, and he doesn't care. Yeah, and just to mention that we worked with Joe Tchaikovsky at MIT on this one, and this one. This is a brand new one, which is a crystalline spin moire supervax. And I'll very briefly mention that quick. And the Gomi systems, Nirmal already talked about these two, so I'm not going to talk about that in the summary. So let's very quickly talk about this singular angular magnetoresistance. This was discovered in Joe Tchaikovsky's lab. And Dr. Ichiro Suzuki was his postdoc at the time. And then we really needed theory, and Leon Balance and Lucille Savary and J.P. Liu worked out the theory. And this classic now paradigm for these days is you need experiments, you need national facilities, you need theory. And so here's what you see is that if you look at the magnetoresistance above the ordering temperature, so this 6 points, going around with magnetic field in the AV plane, it just looks kind of ordinary. There's a little bit of variation. But when you go into the ordered state, you get these spikes. And I should mention that this is just displaced here for visual, so you don't get too confused. But basically, this comes right through it, so the overall level hasn't change much. But you get these big spikes, and they're very sharp, typically 1 degree, and they only occur over limited temperature range. So it's 1.3 Tesla, you start to see it. By 2.2, you got kind of maximum effect, and by 4 Tesla, it's gone. And these also have been displaced, so you can see the different curves. So I'll skip that. So we did the magnetic scattering. Typically, when you do magnetic scattering, if it's a new system, you want to do powder diffraction first, if you can see the peaks, and then you want to make sure you don't miss anything. And then we follow that by single crystals. And here's the answer: is that you have 2 different cerium sites, and they have different sized magnetic moments, but they order antiferromagnetically. But because the moments are different in size, there's a net magnetization system. And then you apply a field along the spin direction. And if it's exactly along the spin direction, you can get a spontaneous symmetry breaking, or you can tilt the field just a little bit, and you get 2 different possibilities where the spins tip over like this, or the spins tip over like that. And so they when you go sweep through this 010 direction, you go from one type of domain to the other type of domain. And what the theorists figured out, and I'll skip the details, but is that if you look at the Fermi surface for these 2 magnetic structures, and they're very strongly coupled, and there are some wild points very close by, that from one side to the other, and you can see kind of the projection here, they don't match up. So when it transforms from one domain structure to the other, the electrons have a really tough time going through that domain wall boundary, and that's why the resistance suddenly shoots up. So that's the answer for this. Okay. Okay, so I just give you some references, and I hear a rumor that these are going to be eventually posted online. So I got the links for both X-rays and neutrons, and a list of publications down here. And with that, I will thank you and ask for questions.
Okay, question.
So about these vortex lattices and the ferromagnetic superconductors, is it always just a simple shift of Q, be not movable gauge, or is there also a broadening of the peaks, or possibly?
Well, we didn't see any broadening, and that's kind of the only ferromagnetic superconductor that, you know, where you have a transition
All right, and that was the
into
only,
that. So, right.
that was the only one that the vortex lattice was observed, it says.
Well, there are many different vortices, but there's only one where it spontaneously, you get a vortex lattice and you spontaneously form additional vortices. And so that should shift the peak. And in fact, it works out well with the magnetization. I have another slide of other vortices, a very pretty slide, I left that out. But it's in, you know, in the PDF that we'll post, I added in a lot of extra detail. No extra charge.
$5, I'm not going any other.
Yeah. Or a cup of coffee. Anyway, I tried to give you, you know, a little flavor for the types of things you can do. Some of them. Instrumentation over the years have changed dramatically, certainly in X-ray, but also in neutrons. What you can do. The basic techniques are.
Do you think that the theory for magnetic X-ray scattering will ever catch up with the theory for neutron scattering?
I tend to doubt it. I mean, because, you know, X-rays, you know, it's very strong interaction, and you have very strong charge scattering in that. So that makes it difficult, but you can get a lot of information now. Well, one of the nice things in X-rays is you can look at a single magnetic peak and do a scan where you with the wave vector along here, just rotate the crystal around here, magnetic peak, and you get the spin direction out from a single magnetic peak, which is really kind of cool. So I think, you know, I mean, it's certainly developing. I don't know, you have to ask the theorists, but yeah, I think it really is complicated. And, you know, I showed the simplest spherically symmetric, you know, the spherical cow cross section, but it gets very complicated and very.
The reason I mention that is because there's a lot of the modern experiments with neutrons require extensive modeling theory to understand. You see a lot of scattering.
Right.
And I don't think with X-rays anybody would ever be model.
Well, yeah. Never say never. Right. Yeah.
You have a question?
Yep.
You mentioned also you could see maybe with neutrons, magnetic textures like fermions. Do you need like an order lattice of fermions?
Yes. Typically, you need an order lattice. Yeah. And that's what you see. I mean, I didn't put an example in, but we did recently a fermion measurement on gallium 84SA, and you see it looks a lot like a vortex scattering.
Oh, and I was also curious, you mentioned crystalline moire superlattice.
Crystalline
Moire, I don't know how it's pronounced.
Trace the word.
The Moire lattice, yeah.
Yeah.
Right.
You mentioned that.
So that's an incommensurate magnetic structure, and it's just been submitted for publication.
This is the European silver.
Right. Yeah. Right. Yeah. And because it's incommensurate, when you look at the magnetic pattern, it forms a Moire lattice like gravity.
Yeah. But it
doesn't spontaneously.
It happens like bulk, or
Yeah, it's bulk. It's a bulk crystal, and it happens in bulk. But you get a plane that forms a Moire lattice.
Yeah.
And then you can see that in the transport. So it's really kind of cool.
Okay, last question.
If you want to study the magnetic structure of single crystals for neutral diffraction experiment, you said it should be less than 100 milligrams. What is the least mass that can be used to measure that?
Which one? Sorry.
So if you want to study magnetic structure of a single crystal for neutral diffraction experiment, it should be less than 100 milligrams, right?
Right.
And what is the least mass that can be used for?
Yeah. Well, that's a good question. So the first point I would say is that, you know, the smaller the crystal, the more difficult to get quality data. So you're always fighting getting enough data. So, you know, if it takes, 3 minutes to scan through, for example, a bright peak, and you get a lot of data in a couple of days. If it takes you 5 hours to do that, you're not going to get nearly as much data. So the minimum is typically micrograms. So in epitaxial thin films, you can look at the magnetic scattering or structural scattering of the film itself, assuming you can separate it from the substrate and measure that. And we've done that. So you can do on epitaxial thin films single crystal diffraction. Again, it's a challenging measurement because you're down in the microgram range. So if you can get up in the milligram range, typically you'll have a lot of good intensity, your temperature dependence, field dependence, whether you want to apply an electric field, pressure, whatever you want to do.
Okay, let's thanks Jeff again.